Welcome to Homework Lib.
So over here we have the following problem in which we're asked to, first of all, name each of the processes and calculate the pressure at each of the states. So first of all, we're going to calculate the pressure at each of the states as nRT divided by B. In this case, we have 22.4 liters, 273 Kelvin, which is going to correspond to a pressure equal to 1 atmosphere at point 1. For point 2, what is going to occur is that we're going to double the amount of temperature, keeping the volume constant. So the pressure applying these conditions is going to give us a result of 2 atmospheres. And finally, for pressure 3, we doubled the temperature, we doubled the volume. So the total pressure would correspond to 1 atmosphere as well as the first process. So with this information, what we can say is that process A is going to be an isobaric process. Process B is going to be an isochoric process, since volume is going to be constant, and process C is going to correspond to an isothermic or isothermal process. Okay, so over here I'm going to start by doing the calculation for part B. In the case of B, what we're going to get is that since this is going to be an isothermal process, the value of the heat is going to be equal to, let me put it down here, for process B, what we're going to get is that the heat is equal to mCb times delta T, and the value for Cb for an ideal gas is going to be equal to 5/2 of R. Okay, so the value over here for the heat would be 1 mole times 5/2 of R times 273 Kelvin. Since this is going to be the constant temperature, sorry, since that is going to be the value for delta T that we're going to have. So the heat for this process is, employing a value of R of 8.314 joule per mole Kelvin, 5,674.305 joules of energy, which is 5.67 kilojoules. So this is going to be heat absorbed by the system. This is going to be positive, 5.67 kilojoules. In this case, the work is going to be equal to 0, since there's going to be no change of volume for this ideal gas. Thus, the change of internal energy, which is Q plus delta U, would be of 5.67 kilojoules. Now, to get the change of entropy, remember that delta S can be found directly for the differential of S. In this case, we're going to use it as a function of T and P. And what we're going to get is that it would be equal to Cp over T differential of T minus R over P differential of P. This is going to be the differential form for S as a function of temperature and pressure. So the value for delta S would be equal to Cp logarithm of T2 over T1 minus R times the logarithm of P2 over P1. For us, this is going to, since the temperature is going to double and the pressure at both points are going to double, this is going to become logarithm of 2 times Cp minus R. Factorizing the logarithm of 2 coming from each of these quantities over here. And what is Cp minus R? Let's remember that for an ideal gas, we know that Cp minus Cb is equal to R. So Cp minus R would be equal to Cp. So delta S would be Cb times logarithm of 2, which is 5/2 of R times the logarithm of 2. This is going to give us as result 8.64 joules per Kelvin. Sorry, it is going to give us a delta S equal to 14.4 joules per Kelvin. So over here we can write down 14.4 joules per Kelvin. Now, for process C, this is going to be an isothermal process. So for an isothermal process, we know that the internal energy of an ideal gas is a function of temperature alone. Since the temperature is going to be kept constant, what is going to happen is that delta U is going to be equal to 0. So over here, we can calculate the work, and the heat is going to be the inverse of that to have the final result. So the work for this process is going to be equal to minus nRT logarithm of B2 over B1. The volume is going to be doubled, so this is going to be 1 mole times 8.314 joules per mole Kelvin times the temperature, which is 546 Kelvin, times logarithm of 2, because the volume doubled down, with a negative sign in front of it, of course. So the result of this would be equal to 3,146.5 joules, which is approximately 3.15 kilojoules, with a negative sign. So over here, we're going to get minus 3.15 kilojoules. Thus, the heat needs to be equal to 3.15 kilojoules. And finally, to get the value for delta S for an isothermal process is going to be equal to, for an isothermal expansion in this case, it is going to be equal to nR logarithm of B2 over B1. So since the volume doubled down, again, this would be equal to 8.314 joules per mole Kelvin times logarithm of 2 times 1 mole. So in this case, the result would be 5.763 joules per Kelvin. In this case, we could also have used the fact that delta S is going to be equal to the reversible heat divided by the temperature for this process. And you're going to arrive to exactly the same formula. So in this case, the result is exactly the same. So over here would be, if you want to divide 3.15 by the temperature of 546, you're going to notice that we would get the same result. So in this case, we can round it up as 5.8 joules per Kelvin. And finally, for process A, which is going to be an isobaric process, what we're going to get is, for process A, the heat would be equal to N times Cp times delta T. Remember that the Cp is going to be equal to 3/2 of R. So 1 mole times 3/2 of R, which is 8.314 joule per mole Kelvin. Oh, sorry, actually, here I just realized that I made a mistake. The value for Cp is 5/2 of R. Yeah, I got it the other way around. Cp minus Cv is, indeed, it is going to be R. So the value for Cv should be 3. Let me just correct the values on the tables. So this should be a 3. This one over here should be a 3. So we would get, sorry about that, the correct value should be 3,504 joules, which is 3.4 kilojoules. So above here on our table, these two values are going to change. Three point four, 3.4, and delta S should be 8.64. Sorry about that. .64. Perfect. And everything else stays correct as before, so that was the only change. Okay, joules per Kelvin. Okay, sorry about that. So over here we would have that the heat is equal to Cp times delta T. So 5/2 of this. So now the value for delta T would be of minus 273 Kelvin. So the heat for this process, if you notice, is actually going to be equal to minus 5,674 joules, which is approximately minus 5.67 kilojoules. Here we have the value for the heat, minus 5.67 kilojoules. Now for the work, what we're going to get is that this is going to be equal to minus P times delta V. The external pressure is going to be kept constant at 1 atmosphere, so this is going to be equal to minus 1 atmosphere multiplied by the change of volume, which is a reduction of minus 22.4 liters. And we need to use the conversion factor that 101.325 joules is going to be equal to 1 liter atmosphere. So the work corresponds to 2,269.7 joules, or approximately 2.27 kilojoules. We can go up right here, 2.27 kilojoules. Now we can add minus 5.67 plus 2.27 to get the value for delta U, which would be minus 3.4 kilojoules. And finally, for the calculation of delta S. And finally, for this final process, which is going to be an isobaric process, the change of entropy can be written as NCP logarithm of T2 over T1. So this becomes n times Cp logarithm of 2 since logarithm of 1/2 since the temperature is going to be decreasing from 546 to 273. Okay? So with this, our result would be, remember that the value for Cp is going to be equal to 5/2 of R, giving us a result of minus 14.41 joules per Kelvin. 0.41 joules per Kelvin. And with that, it will be all. Now we just need to add up all of the quantities over here to know the overall heat, work, and delta U for the whole process. So in the case of entropy, we're going to have 8.64 plus 5.85 . Oh, sorry, over here, apparently I made a transcription error. It was 5.76, not 5.85. 5.76. Over here, we're going to get a total change of entropy of 0.01 joule per Kelvin, or essentially 0 joule per Kelvin, because this is going to be a reversible process. So any rounding error should come from the rounding on the units on each of the cases. For delta U, it is also going to be equal to 0. The total heat of the process would be 3.4 plus 3.15 minus 5.67, which gives us 0.88 kilojoules. And we're going to get on work minus 3.15 plus 2.27, which is negative 0.88 kilojoules. So as expected for a reversible process, on the whole cycle, the change of entropy and of internal energy should be equal to 0. And with that, it would be all. Thank you very much and have a good one.